Hi, great to see you, and very welcome to the course Fundamental TLS Transport Layer Security. My name is Cyril Gassi. I'm a computer scientist from ETH Zurich. I work as a cybersecurity expert for a large multinational and globally operating company, and I'm a cryptography lecturer at a Swiss university. TLS, the Transport Layer Security Protocol, is the successor of the by now deprecated Secure Sockets Layer Protocol SSL. The newest version of the TLS protocol is TLS version 1.3, which is defined in RFC 8446, released back in the year 2018. This RFC 8446 defines in its introduction that the primary objective of TLS as a protocol is to construct a secure channel from an insecure channel between communicating peers that have never met before. A secure channel is understood to be a channel that provides both confidentiality as well as authenticity to the data exchanged. With this understanding, an insecure channel is then a channel that is neither confidential nor authentic, and a good example of such an insecure channel would be the channel from the laptop of Alice through the internet to a web server, like the web server serving the site IBM.com. Without any additional protective mechanisms, the communication between the laptop of Alice and the IBM web server would often be based on HTTP wrapped into TCP/IP packets. None of these protocols provides cryptographic confidentiality or authenticity to the data exchanged, meaning that with plain HTTP over TCP/IP, the data exchanged between Alice and the IBM web server could simply be eavesdropped on or tampered with. What makes TLS as a protocol now truly fascinating is that TLS allows for the construction of a secure channel between communicating peers, even if the communicating peers involved have never met before. This is amazing, and I invite you to join me on this course in order to get to see and understand how TLS managed to achieve this. To implement the just presented, clearly defined objective of TLS, TLS as a protocol has to make use of various cryptographic primitives. Many of these cryptographic primitives are parameterized, and one of the first steps that communicating peers need to do in order to establish a TLS connection is to agree on a specific configuration of all the cryptographic primitives involved. Within TLS, these specifications are called cipher suites, and I listed two example cipher suites on this slide. The first cipher suite is a cipher suite of TLS 1.2, and the second cipher suite is a cipher suite of TLS 1.3. The TLS 1.2 cipher suite reads TLS ECDHE RSA with AES 256 CBC SHA 256, and the TLS 1.3 cipher suite reads TLS AES 256 GCM SHA 384. The reason I present these TLS cipher suites so early on and before we even properly started with the course is that understanding these cipher suites is essential to understanding the inner workings of a specific TLS connection and the security a TLS connection is capable of providing. However, even though highly essential, it's also clear that these cipher suites are quite cryptic in appearance, especially when looking at them for the first time, and can easily lead to confusion about the actual specification of the cryptographic primitives if the cipher suites are not properly understood for the elements that they specify. I invite now everyone to pause the video at this point and to try for yourself if you can explain what each of these two example cipher suites specifies. This is by no means meant to expose anyone's lack of knowledge or understanding of the subject, but as a motivational teaser, as I'm very confident that everyone that comes along with me on this course will, at the end of the course, be able to fully explain both the cipher suites of TLS 1.2 as well as the cipher suites of TLS 1.3. So again, I suggest you pause the video now and have a go at explaining the two cipher suites presented. What are the goals of this course? The first goal of this course is that once you complete this course, you should have a good, intuitive understanding of the primary objective of TLS presented just 2 slides ago, and how TLS ultimately achieves this objective. The second goal of this course is that you should have a good understanding of the differences between TLS 1.2 and TLS 1.3, both in terms of the protocol itself, as well as the cipher suites offered by each of the TLS versions. The third goal of this course is then that once you complete this course, you should have a good understanding of the security implications coming out of using a certain TLS version and a certain cipher suite. The last goal, listed in orange at the bottom of the slide, is a goal that I have for myself from an educational perspective for this course. For myself, and as the instructor of this course, it's important that I will continuously try to animate you to stay engaged and to try to develop many of the ideas and concepts jointly together with you as my audience. In terms of actual content, this course first starts with a chapter providing the essentials of cryptography, just enough to later on understand the cryptographic mechanisms taking place within TLS. The cryptography of TLS evolves primarily around the 4 classic security goals: confidentiality, integrity, authenticity, and non-repudiation. As such, this course will have a look at each of these security goals and will provide a recap of the cryptographic concepts and primitives existing that can help implementing these security goals in digital information systems. For confidentiality, we will get to know symmetric encryption with AES, asymmetric encryption with RSA, hybrid encryption, and the ephemeral Diffie-Hellman key exchanges, DHE and ECDHE, which are key exchanges allowing to provide what is known as forward secrecy to data encrypted. For integrity, we will get to know cryptographic hash functions and we'll get a recap of the security of MD5, SHA-1, SHA-2, and SHA-3, which are 4 of the most widely used cryptographic hash functions. Going into authenticity, we will get to know message authentication codes, authenticated encryption with the encrypted and MAC approach, and authenticated encryption with associated data with the GCM block cipher mode of operation. For non-repudiation, the 4th classic security goal of cryptography, we will get to know digital signatures, which come across in different flavors, such as digital signature systems based on RSA, DSA, ECDSA, which is DSA based on elliptic curves, or ED255, 19, and ED448. Following the first chapter providing the essentials of cryptography is then a chapter dedicated to TLS as a protocol itself. This chapter starts with a brief history of TLS, whose origins root back into the secure socket layer protocol SSL, then general TLS protocol information such as the locality of TLS within the TCP/IP model, a high-level TLS protocol structure, and the structure of TLS cipher suites is presented. This is followed by a reasonably in-depth presentation of the handshakes of both TLS 1.2 and TLS 1.3, with the handshakes being the initial sub-protocol of TLS responsible for negotiating all the necessary cryptographic parameters required to construct the confidential and authentic channel between the communicating peers. The third major chapter of this course is then a chapter presenting miscellaneous topics around TLS. First, we will have a look at the efficiency of the TLS 1.2 and TLS 1.3 handshakes, which is then followed up with an investigation on the caveats associated with TLS session resumptions and pre-shared keys. Then we will have a look at whether backwards compatibility is a thing within the TLS protocol and how the version negotiation mechanism works within TLS. Next one up is then a comparison of the cipher suites supported by TLS 1.2 and TLS 1.3. As we will see, TLS 1.2 has a large set of supported cipher suites, which on one hand gives TLS 1.2 a high degree of flexibility, but on the other hand also leads to a large attack surface. This realization then leads us to investigating some of the major attacks on TLS, such as Lockjam, Lucky 13, Sweet 32, Crime, and Heartbleed. Even though these attacks are interesting subjects to be studied in and by themselves, the major takeaway from these attacks is a set of recommendations on TLS cipher suites, which will be presented for both TLS 1.2 as well as TLS 1.3. Next topic up that we will then investigate is whether the application data exchanged within TLS is protected with authenticity only or non-repudiation. This is followed by a lesson on the key differences between the role of a TLS client and the role of a TLS server, once on the level of the TLS protocol itself, but once also on the level of the X509 certificates used by both the clients and the servers within a TLS connection. Then an interesting lesson follows on the topic of whether TLS necessarily needs to be used together with certificates, or whether there is a way to use TLS without certificates, and what the security implications of such a TLS use without certificates would be. Last in this chapter on miscellaneous TLS topics is then a lesson that investigates the differences between TLS master secrets, pre-shared keys, and the encryption keys used to protect the encapsulated application data, and which will explain how the links between all these secrets and keys are given by the pseudorandom function PRF and the HMAC-based key derivation function HKDF. I think that throughout this course on TLS transport layer security, we have a lot of very interesting topics to discuss ahead of us, so let's get started with the course.